Hello, and welcome to the sixth exciting installment of Digital Design and Computer Architecture. In this chapter, we'll be talking about architecture. So architecture is the programmer's view of a computer. It's the set of instructions and memory that a programmer needs to know that defines a computer. If you build two different computers with the same architecture, they could have entirely different implementations but still run the same program. We'll also be looking at the level above a little bit, looking at software and operating systems that run on an architecture. We'll start by focusing on assembly language programming, which is the native language of the machine, and how to get into translating programs from a language like C into assembly language. Then we'll go into machine language, the ones and zeros that actually run on the hardware. We'll talk about addressing modes. We'll talk about the process of compiling, assembling, and loading program, and various odds and ends. So previously, we've been working at the low levels of abstraction. We started with devices, worked our way up to digital circuits and logic, and now we're jumping up to the opposite end, architecture, the programmer's view of the computer. And then in Chapter 7, we'll work our way back down to microarchitecture to meet in the middle and look at how to build hardware that actually implements an architecture. So the instructions in assembly language are the commands in the computer's language. And they come in two formats. Assembly language is a human-readable format of these instructions, and machine language is a bunch of ones and zeros that's computer-readable. There are many different architectures in the world, and this book is focusing on the RISC-V architecture. The RISC-V architecture was developed by researchers at Berkeley starting in 2010. It's the first widely accepted open source computer architecture, so it can be used freely by anybody. It can be enhanced, and it's gaining a lot of traction in industry right now. It's a hot thing, so we're focused on that one in this class. But once you've learned one architecture, it's really easy to learn all the others. Some of the originators of computer architecture, Kristi Sonovic from Berkeley was a pioneer on developing RISC-V and is presently chairman of the board of the RISC-V Foundation and co-founder of SI5, which is a company that is commercializing RISC-V. His colleague David Patterson is a longtime computer architect at Berkeley who co-invented the reduced instruction set computer notion back in the 1980s. He was also a founding member of the RISC-V team. David Patterson was a co-recipient of the Turing Award for pioneering the quantitative approach to design and evaluation of computer architectures. And his colleague John Hennessy from Stanford was also co-recipient of the award and co-author of a classic textbook titled Computer Architecture. So prior to Hennessy and Patterson, computer architectures were often evaluated based on how elegant they were. For instance, an architecture that might be able to run Pascal or Lisp programs directly. And Hennessy and Patterson made the bold statement back around 1990 that computer architectures should be evaluated based on how fast they can run your program. That led to the notion of reduced instruction set computers, where instead of having the largest set or most flexible instructions, they simplified to a minimal set of instructions that were capable of running whatever program. And because it was simplified, they could be built with really fast, efficient hardware and could run at much higher frequencies and deliver much higher performance. So RISC computers in the 1980s revolutionized the field of computer architecture, and Hennessy and Patterson's book has been a classic. It's gone through many editions. They also wrote a textbook titled Computer Organization and Design that presents the microarchitecture in a way very similar to this book that's inspired this book. So Hennessy and Patterson articulated four main principles for design. First is that simplicity favors regularity. So keeping things simple and having as few special cases as possible is good. The second one is make the common case fast. Look at what your architecture spends most of its time doing and make those cases really fast. Number 3 is that smaller is faster. If you can build an architecture with fewer instructions, fewer registers, then it will be able to run those faster. But finally, number 4, good design demands good compromises. So instead of sticking religiously to the first 3 principles, occasionally you do have to make compromises for the sake of efficiency.